the last class we had started with the device characteristics or the output characteristics. So I had written a few characteristics. The first one was Li, light current characteristics, or IP characteristics. The second one Li, light current characteristic, and wavelength distribution or spectral distribution, wavelength spectrum or spectral distribution, angular distribution or radiation pattern, I am just recalling, or radiation pattern, and the fourth one is modulation bandwidth. These are some of the important device characteristics, modulation bandwidth. We started discussion on the Li characteristics, and we know that the optical power generated given by an expression P output, P out optical is equal to eta external into I by E into h nu, which you can also write eta external into h nu is C by lambda. So h C by lambda is by E is 1.24. So 1.24 into I by lambda, where lambda is in micrometers. The output power P out is equal to eta external into 1.24 I by lambda. I is the current and P is the optical power, P out. So which obviously means that the optical power is proportional to the current. So if you plot I versus P optical here, then we are expected to get a linear curve. But as I said, in practice it deviates at higher currents. At higher currents it deviates from the linear relation, and we were discussing why this nonlinear behavior or deviation from the linear characteristics. So typical numbers may be 50, 100, 150 milliamperes. You should always be familiar with the typical numbers I in milliamperes, and P optical power, this could be 100, 200, 300, 400 microwatts. This is microwatts. Of course, there are LEDs which can give milliwatts of power also, but typical LEDs would give this kind of variation. So we were interested to see what is the reason for this. I had listed three different reasons. One, the Joule heating. I am quickly recalling what we had discussed. Joule heating. Second, carrier leakage loss. So carrier leakage. And the third one is stimulated emission loss. Stimulated emission loss. So these are the three major reasons. Joule heating we have discussed. It's quite clear that as you pass higher current here, as you pass higher current, the I square R loss leads to heat generation or heating of the device. Heating of the device leads to availability of much more phonons in the material, and therefore the non-radiative recombinations start dominating over radiative recombinations, and consequently eta external, which contains, recall that this eta external contains eta external is equal to eta I into eta extraction efficiency. So eta I drops down exponentially with temperature, and therefore eta external drops down, and therefore eta I drops down exponentially, and therefore the power generated or power output drops. So these are so that is Joule heating. The second one, carrier leakage. So today we will discuss carrier leakage and the stimulated emission loss. And then go over to the spectral distribution and angular distribution. Some of these characteristics I discuss in little bit more detail because similar considerations are valid for laser diodes. So what is this carrier leakage? Second point, carrier leakage. If you take a PN junction, then the band diagram PN, or you could take the heterostructure also, is one and the same. So before biasing, this is E, X, EV, EC and EF before biasing. So there are plenty of electrons here and plenty of holes here. When you forward bias, this device, that means to the P end, so Pn, to the P end you apply, you forward bias the device, which means you are lifting this band up. So I draw this again. Just let me redraw it. The dotted lines indicate the original position. So you have carriers coming here, plenty of carriers and plenty of holes here. Which means in the same position, physical position X, so this axis is X, this axis is E. In the same physical position, you have plenty of electrons and holes which recombine, that leads to an external current. However, as you forward bias this stronger, that is, as you increase the injection current, which means you are biasing it stronger, the carriers here, electrons, do not see any more barrier. Please see, this is the potential barrier which was blocking the electrons. Now, when you lift this up, that is, when the injection current becomes large, the carriers can simply go over from here like this. This means, please see here, there are plenty of vacant states and there is no barrier. Therefore, and remember that this end we have applied positive bias, which means this end is positive. So the electrons here just get collected by the electrode at the other end. They do not recombine with the holes because there are plenty of vacant states here and there is no potential barrier, and therefore the electrons simply rush to the other end because that is the positive end and get collected. Exactly same thing happens here. The holes can simply go to the other end. When do we get photons? Photons we get if the electrons combine with holes. So when you forward bias, electrons combine with holes, leading to generation of photons. But if the electrons are directly collected by the electrode at the other end, there is no generation of photon. This is called carrier leakage, leakage of carrier. So carrier leakage from this end. So although you are passing a higher current, recombinations are taking place, generation of light is taking place, but some amount of carriers leak without leading to recombinations and therefore without contributing to generation of photons, and that leads to the saturation. Second effect, carrier leakage loss, which leads to saturation, is this. We go to the third very quickly, stimulated emission loss. This is a little different. Stimulated emission loss is a loss for surface emitting LEDs, but it's a gain for edge emitting LEDs. We'll see what is this stimulated emission loss. So let me erase this. So recall the structures, device structures of surface emitting LED and edge emitting LED. In edge emitting LED, you have a channel where optical confinement is taking place. So stimulated emission loss. I come to the next point, stimulated emission loss. Very quickly, if you recall the structure of the LED, the cross section that I am showing, I am not showing all the layers. So just let me show the active layer here. So here is the active layer. In surface emitting LED, light which is coming out is what is the output. The output that we get is the light which is coming out like this. Whereas in edge emitting LED, the light which is generated and trapped inside because of optical confinement is the output that we get. The edge emitting LED, the output that we get is the optically confined output. It is optical confinement is because this material is a lower band gap material, therefore the refractive index N here is higher compared to the cladding layers which have refractive index a little lower, N2 less than N1. They are, recall that they are high band gap materials on the side because we formed double heterostructures. So these are the cladding materials, this is the active material. So light is confined because of total internal reflection. So we get output from the edges. So this is ELED, edge emitting LED, and this is SLED. Both of them are double heterostructures. Double heterostructure is required because we want to minimize the reabsorption losses. One, please see, recall the points. Why do we need double heterostructure? Three basic points are carrier confinement, because to get larger delta N so that the Fermi level can move up, the separation between the Fermi levels can be large for a given current. Second point is optical confinement, because light can be trapped. This is not useful for surface emitting LED because you don't want any confinement, you want it to come out. So this is optical confinement is useful for edge emitting LEDs and, as we will see later, semiconductor lasers. The third point is reabsorption losses. To minimize reabsorption losses. So these 2 points are very important for both the LEDs, and therefore you have to use a heterostructure, but there is optical confinement. As you pump harder, you are pumping harder, increasing the injection current means you are increasing the separation between the quasi-Fermi levels, EFC and EFV. This is EC, this is EV. What I am drawing is the energy band diagram in the active region. So this is in the active region. Okay, let me draw this, because Fermi level we normally draw with the dashed line. So let me draw. So if I draw the energy band diagram in the active region, there is a separation of the Fermi level because of injection current or forward biasing. If you pump harder, means if you inject more, then the Fermi level separation increases. And you know that when the separation between the Fermi level is larger than Eg, then stimulated emission will take over absorption. The probability of emission will be more than that of absorption, and stimulated emissions will take over. As you start increasing this separation, stimulated emission starts slowly increasing. Although it has not yet taken over, but it is increasing. And therefore, a photon which is traveling in this direction, light generated and traveling in this direction, will start stimulating additional photon. So if I zoom this portion, just zoom that portion, light which is a photon which is traveling like this will stimulate further stimulated emission, and therefore this will start building up. It will further build up. This is exactly the laser action. So almost a laser like action. Stimulated emission has started increasing as EFC minus EFP separation increases. It is still not reached the stage where it is dominant, but it has increased. So in the case of an edge emitting LED, what would happen is stimulated emission will also lead to, there is spontaneous emission due to which light is coming, that is the LED operation, but stimulated emission is also contributing to the light generation, and therefore the net generation would increase with increase in separation between these. And therefore what would you expect in the case of an edge emitting LED? We should expect, if this is the case, then I should expect it to go like this. This is P versus I. I have not shown that yet, because there are three reasons why it was saturating. The two reasons which we discussed are still dominating, and therefore we are not able to see this even in an edge emitting LED. I will return to this, but as far as SLED is concerned, SLED, surface emitting LED is concerned, this stimulated emission is definitely a loss, because now more and more photons are generated in this direction and light is going to the sides. So the total amount of light coming out reduces. It is not proportional to the current that you are injecting, and this is called stimulated emission loss. To summarize, stimulated emission loss is a loss for surface emitting LED, but is a gain for edge emitting LED. However, even in an edge emitting LED, normally you will see saturation is doing this. Normally, you would not see this, but you will see this if you go to low temperatures. If you reduce the temperature, you will indeed see a graph like that. So what I am now plotting is characteristics, temperature dependent output characteristics of a superluminescent diode. These are experimental curves reported in the literature. I will first draw the graph and then explain. The current that I am plotting are now hundreds of milliampere, 100 milliampere, 200 milliampere, 300 milliampere. The power here is typically so this is log scale 0.1 power in milliwatt. 0.1, which means 100 microwatt, 1 microwatt, and 1 milliwatt, 10 milliwatt. Power in milliwatt, 1 milliwatt, 0.1 milliwatt, which is 100 microwatt, 1 milliwatt, and 10 milliwatt. These are typical numbers for superluminescent diode, SLD. This is SLED, surface emitting light emitting diode. This is ELED, and this is SLED, superluminescent diode. Or sometimes it is also called super radiant LEDs. Super radiant LED. The structure of a superluminescent diode is the same as that of an LED, almost the same as that of an LED, of a ELED, except that typically this length is little longer in the case of a, so that this effect becomes dominant. Please see, the stimulated emission gain will be more if the length over which the photons are traveling is larger. In a gain medium or in a medium where there are photon generation taking place, if you have sufficient length, then the amount of light accumulated, generated and accumulated because of stimulated emission will be more. Please see, in the case of a surface emitting LED, even though a photon which is traveling like this induces stimulated emission, within no time it is out of the active region. Whereas a photon which is traveling in this direction, it has plenty of time in the sense plenty of medium, that active medium available to create more stimulated emission. That is why this one, you see, more stimulated emissions possible, and therefore if you increase this length, then stimulated emissions can be very significant, and therefore a superluminescent diode is primarily an edge emitting LED. Typically LEDs have 100 to 300 micrometer typical LED length. But if you take superluminescent LEDs, SLDs, typically have 500 to 700 micron L. The L length is typically large, 300, 500, 600, because that will enable a longer optical path where you can have stimulated emission. So this is a superluminescent diode. Please see, at normal temperature, it is still saturating, or the power is deviating from the linear behavior just like in an LED. However, when you cool, the phonons go down, and therefore you have kept the device at 20 degrees centigrade, therefore the Joule effect is not there, Joule heating effect is not there, because you have maintained the temperature at 20 degrees centigrade. So even if the current is increasing, the Joule heating effect is not there, and you can see a curve which is increasing in an upward direction because of the stimulated emission gain. These are measured curves in superluminescent diodes. You can have power increasing upward. You can see a change in slope here because of stimulated emission gain. But normal surface emitting LEDs and edge emitting LEDs at normal temperature will have always a nonlinear behavior which is reducing or deviating away from the linear region. So I hope the 3 points are clear, that stimulated emission gain for ELED, stimulated emission is a loss for SLED, and we are making use of that to generate superluminescent diodes. The structure of a superluminescent diode and or an edge emitting LED in general is almost the same as a semiconductor laser, except that there are no cleaved surfaces at the ends which act as mirrors, mirror-like ends in the case of a semiconductor laser to provide the necessary feedback. You do not need that feedback in the case of LEDs, because if feedback is there, then it will start oscillating. So we will discuss the semiconductor lasers in more details at a later stage. So let me come to the next characteristic, that is spectral distribution or wavelength spectrum. Because you would come across somewhere superluminescent diodes, and you saw that the current that is passing through are relatively large, 100, 200, 300 milliamperes, because the device is long. Therefore, there is more current which is flowing through the device. Current is flowing from the top because the electrodes are here, and because the device is longer, there is more current which has to flow to create the same delta N, the same concentration. Because if the volume is larger, length is larger, therefore volume is larger. So we come to wavelength spectrum. Spectral distribution or wavelength spectrum. Any source if you plot the intensity distribution of a source, you generally see that it has a finite width, and the full width at half maximum FWHM. So FWHM, full width at half maximum, that is, if this is the maximum, then half of it full width in lambda. So this is called delta lambda, is called the line width. And this is called the line center. The lambda 0 or lambda p is sometimes called line center. This is the line. Why is this called sometimes line? Because traditionally, if you see the spectrum of any substance, any material, gas, you will see spectral lines. If you see under a normal spectrometer, you will see, if you take for example mercury lamp, you will see lines blue, violet, green, yellow, different lines you will see. So what we call them as spectral lines. So this is what I have plotted is lambda versus the position. We are not measuring in a spectrometer, we don't measure intensity. What we are measuring is the angle theta where it comes, because our objective is to determine the wavelength. So then we use d sin theta equal to n lambda and determine the wavelength. So these are called spectral lines. So this is line. If you now resolve one line under a high resolution spectrograph, then you will see that this line is actually, it is like zooming. So this line is actually like this. So the same thing in wavelength, you are zooming now, and then you see that lambda versus I of lambda, if you measure the intensity lambda, then you see this. This is what I have plotted. And therefore, the center of that line is called line center. So this intensity distribution is a line which is expanded in the wavelength scale. And therefore, this is the line center, this is the line width, this is the width of the line. So this is the reason why you use these terminologies, line width and line center. So we want to see what is the spectral distribution of an LED. Recall what we have studied. The spontaneous emission, light generation in an LED is primarily due to spontaneous emission, and the rate of spontaneous emission will indicate the rate at which photons are emitted, and therefore the intensity is determined by the spontaneous emission spectrum, spontaneous emission rate. So RSP of nu, you recall, this we have derived already, recall, RSP of nu is equal to D0 into h nu minus Eg to the power half into e to the power minus h nu minus Eg h nu minus Eg by kT. An expression of this form, then we said let this be x, so that we wrote this as d0 into x to the power half e to the power minus ax, where a is 1 by kT. Right, this is a kind of variation. And then we plotted this and we got a variation which, so what I have plotted is h nu versus RSP of nu. Every spontaneous emission generates one photon, and therefore the rate at which spontaneous emissions are occurring will also be the rate at which photon generation takes place. And therefore, the output spectrum is basically determined by RSP of nu. And we have seen that this peak here, so this starting point is Eg and the peak corresponds to Eg plus half kT capital T temperature here, and the line width here we had an exercise. So this line width, because this is energy axis, delta E is equal to H into delta nu was equal to approximately equal to 1.8 times kT. From this you could determine what is delta lambda. So delta lambda is approximately equal to 1.45 into kT into lambda p square. Lambda p was corresponding to this peak. So this Eg, so h nu p is equal to Eg plus half kT. So nu p here is C by lambda p. That is the peak at which, the wavelength at which the peak occurs. So this gives you the line width. In this expression, please remember that this delta lambda is in micrometer, this kT is in eV, and this lambda is also in micrometer. So micrometer square. The question is, how did we get this expression? We had an exercise from which you had to find out the full width at half maximum here. Okay, so this was the maximum here. So you had to find out what is the full width at half maximum. So if you find this out, what is the full width at half maximum, you will get this. How to find this out? This is not analytically solvable. You have to numerically solve this, either graphically or numerically. Then you can find out that this separation here, this axis is energy, this you call as E2, this you call as E1, then delta E, E2 minus E1, which is also equal to H into delta nu, is equal to this. This you have to determine numerically. And then in this you simply substitute for delta lambda, because delta nu is C by lambda square into delta lambda, and that lambda is corresponding to the peak, and this is the expression. Okay. If you still find it difficult, we can discuss about this. So the line width, the point is delta lambda is given by delta lambda is equal to approximately 1 into lambda p square. Two things you note here. Delta lambda here is proportional to T. The width is proportional to temperature, line width. Second, delta lambda is proportional to lambda p square. And let us take an example, what kind of numbers that we get here. Let us see. Example, at room temperature, so kT is equal to 0.025. Let us say a gallium arsenide LED is emitting at 800 nanometer. That is, lambda p is 800 nanometer. I am just taking an example. Gallium arsenide LED is emitting at 800 nanometer. Then you can find out what is delta lambda. Just to have an idea about what kind of numbers that we have, is 1.45 into 0.025 into, this has to be in micrometer, therefore 0.8 square, so 0.64, lambda p square is 0.64, and check how much is this, so many micrometers. So this, if I say 1.5 approximately, which means this is, how much is this? We can simplify this. 0.64 into 1.5 is approximately 1, and therefore this is 0.025 approximately equal to 0.023. Okay. So he has calculated 0.023 micrometers, that is 23 nanometers. So delta lambda is equal to 23 nanometers. Typically, in the visible region, of course, you can see that instead of lambda p at 800, if you take a visible LED 600 nanometer or 630 nanometer, then you will have even less. So typical values of delta lambda is of the order of 20 to 30 nanometer in the visible. And is of the order of 50 to 100 nanometer in near IR. That is 1.5 micron. Typically, this is the kind of numbers that you would get for LEDs. All right. So I come back to this graph. If this is the spectral distribution that we have got, if you increase the temperature, what do we expect? We expect that, let me first plot and then you see whether what I have plotted is right. So we expect this to shift to right, because Eg plus half kT, T is temperature. Therefore, as I increase temperature, the peak is shifted to the right. And what else do we expect? The delta lambda will also increase because it is proportional to temperature. Therefore, the full width at half maximum, now you see the full width at half maximum, it will be more than the original. Full width at half maximum, it is shifting to the right. And the amplitude is also increasing. Why did I show that the amplitude is increasing? Because this D0, if you see the expression for D0, this has some terms into e to the power minus Eg by 2 kT. The D0 contains some terms here. I can give you exactly the expression for D0. So D0 is given by 1 over tau here, and 2 mr, we have derived this, 2 mr to the power 3 by 2 divided by pi h cross square into e to the power Eg by kT. Eg by kT. So temperature increases, exponent decreases, e to the power minus an exponent which is smaller, which means D0 is larger. Temperature increases, tau decreases, therefore D0 is larger. So D0 is larger, that's why it is going like this. So you expect an LED, if you increase the temperature, to go up like this. Means more radiance if you increase the temperature. In practice, this is not what you see. So what if I were to plot this in the wavelength scale? Let me plot. This is an important point. I had to make an important point here. That is, in practice, so if I convert this into wavelength, this is lambda versus I of lambda or RSP of lambda, which is proportional to I of lambda, intensity. You should expect corresponding to lambda g here. So this is lambda g. Lambda g corresponds to Eg, band gap. So if I want to plot with respect to lambda, I expect that theoretically we should expect a curve like this, and at a higher temperature we should expect a curve like this. So this is lambda p1 corresponding to this is at temperature T1, this is at temperature T2, which is greater than T1. Is this graph clear? It is the same graph, it is in the frequency domain, this in the wavelength domain. Higher energy corresponds to lower wavelength. So that's all. And the peak is shifted to lower wavelengths. Peak is shifted to lower wavelengths, but the peak, this is expected from what we have done, the theory that we have done, but this is not what you get. In practice, what you get is here. And we need some explanation, that's why I am plotting this now. This is one of the experiments reported in the literature. I do not remember the reference. This is for gallium arsenide LED. So this is at 10 degrees centigrade, this is at 30 degrees centigrade, and this is at 60 degrees centigrade. Measurements. This wavelength here is about 0.85 micrometer approximately. This is 0.87 micrometer and this is 0.88 micrometer or 885, something like that. Approximate number. So what I have plotted is I of lambda versus lambda wavelength at 3 different temperatures for a typical gallium arsenide LED. So what do we see? One, the peak wavelength is shifting to lower energy. Here it is shifting to higher energy, which means we expect it to shift to lower wavelengths, smaller wavelengths, but it is shifting with the temperature to higher wavelengths. One. Second, the peak, instead we expected the peak to go up. This is at a higher temperature, this is at a lower temperature as per the theory that we have. But this is what you actually see in practice. What could be the reasons? Obviously, our theory has not taken into account several things, and that is why you are seeing this completely opposite behavior. This is going up, but actually the peak is coming down. This is shifting to lower wavelengths with higher temperature, but this is measured, practical. We have obviously missed something. And this is what I want you to keep in mind. And there's an important lesson in this, and that is in certain derivations we make certain approximations or we do not take into account certain aspects. A result could be completely opposite when you take care of those aspects, and this is what this simple experiment demonstrates. First point, band gap of a semiconductor Eg is a function of temperature. We have not taken care of this. Band gap decrease, for example, if you take gallium arsenide, band gap is 1.52 eV around 0 K, and 300 K room temperature, this is 1.42 eV. So the band gap is temperature dependent. You can find there are empirical expressions which are given. You can see there is a very good book by Cassie and Panish. Please, you may refer to this. Cassie and Panish is there in our library. Panish, heterostructure lasers. There are two volumes, volume part A and part B. So there is temperature dependence of gallium arsenide. Let me write Eg for gallium arsenide, which is for temperature dependent. It is listed for almost most of the useful semiconductors, but I am writing only for gallium arsenide. It is given as 1.519 minus, this is an empirical formula, 5.405 into 10 to the power of minus 4 into T square divided by T plus 204. T plus 204. So what you see is, as temperature, this is at 0 K, put T equal to 0 and this is 1.519. That's what I have written here, approximately 1.52. So what you see is the band gap decreases with temperature for a semiconductor. As temperature increases, band gap decreases, means the energy decreases. That is why the wavelength is increasing. This peak is shifting because peak comes at Eg plus half kT. Remember, kT is a very small quantity. From 10 degree, so 30 degree it is 300, 303. 10 degree it is 283 and 60 degree it is 233. So it's a small difference in change in this T, but Eg changes quite a bit. Eg has a dependence which is more compared to this kT. Therefore, although kT was shifting to higher energy, but the band gap Eg itself is decreasing. Eg is a function of T which is decreasing. That is why the net effect is it shifts to the higher wavelengths or lower energy. Why the peak is going down? Second question, we expected this, but the peak is going down. Peak is going down primarily because of, as temperature increases, eta I drops down exponentially as temperature increases. Eta I drops down, and eta I drops down means the rate of spontaneous emission goes down rapidly. Rate of spontaneous emission which leads to generation of photons. Please see, recombination takes place. Tau in the expression there, this tau contains tau r and tau nr. And the relation is 1 over tau is equal to 1 over tau r plus 1 over tau nr. As temperature increases, tau decreases rapidly because tau nr decreases. And therefore, eta I is equal to, we have this expression tau by tau r. Tau decreases rapidly because tau nr decreases rapidly. Why tau nr decreases rapidly? There are non-radiative transitions which increase rapidly as temperature increases because phonons are in much larger number. And therefore, this decreases, leading to a decrease in this, and therefore eta I decreases. And therefore, the generated photons go down with the increase in temperature. And therefore, you have this decreasing. We have not taken care of the dependence of eta I. In our earlier derivation, we did not take care of dependence of eta I on the intensity. The third point is, you see that this is spreading. This is as per our finding because this spreads as, because the delta lambda is proportional to T. So this you observe in practice. What is the physical reason for this? Mathematically, we see that delta lambda is proportional to T, but physically what is happening? Let me quickly show this carrier distribution, the physical variation, and then I will stop. At a particular temperature, we have carrier distribution, which is this. There are different ways of illustrating this. One of the ways is what I am showing. At a particular temperature, this is what have I plotted, N of E. Recall, this is what we had discussed in the first part of the course, carrier distribution, which was a product of density of states multiplied by the probability of occupation, F of E. Recall that F of E itself at a particular temperature, if F of E varies like this, then if you increase the temperature, this distribution, so for a lower temperature, it will be like this. So this is the Fermi energy, EF. This is F of E at temperature T2. This is F of E at temperature T1, which is lower than T2. And this leads to a spread in the carrier. So this distribution here spreads like this. This distribution here spreads like this at a higher temperature. So this is T2, this is T1. When the distribution spreads, the distribution over which photons emitted will also become wider, because a photon, an electron sitting here can combine with the hole sitting here, giving out photon of energy h nu, this gap. An electron which is sitting here, now electrons are even here. Electron which is sitting here can combine with the hole which is sitting here and can give a higher energy, which means the spread has increased. That is why you have a larger spread at higher temperature. This is the physical reason, because of carrier spread in the two bands. So this is about the wavelength spectrum. It's a very important characteristic of any source. So expected, and when you do an experiment, if you find the result is somewhat different than what is expected, then one has to give a thought that why it is different and what is it that you have not included. So now we are able to explain with the inclusion of Eg, a function of time, we are able to explain this, which was not as we saw earlier. I think I will stop here, and we will continue in the next class.